Today, let us talk about the Huffman encoding tree. So, if we look into the big map, we will understand that the Huffman encoding tree is still inside of the scope of the binary tree. So, of course, it is a tree, it is a part of the graph theory. However, it is totally different from the binary search tree as well as the binary heap that we discussed earlier. So, what is a Huffman encoding tree? To understand it, we need to discuss about the zip or the text compression program. So on a computer, changing the representation of a file so it takes much less space to store and or less time to transit. So let's take a look of an example. If we look into data that I have, so this is the research data I'm using, which discuss about the wine in Bordeaux area for 21st centuries. This file contains about 170 megabytes. So you can see that it is actually quite a large data. Therefore, when I try to do research and I'm trying to work with my students or collaborators, occasionally I need to email this data to other people. The question is that for like UCA's Gmail system, to send a file as big as 170 megabytes, it takes a while. At the best case scenario, most of cases they will transit fail or be blocked by the server of the UCA. And therefore, what I need to do is basically I need to zip it. So you can see that if I'm trying to zip the file, so I'm deleting that file and therefore I can be able to zip the file. So when I'm trying to zip a file, you can see that I'm trying to use the RAR. It takes actually probably like 2 seconds. And then it is able to convert this large amount of data into a much smaller. From 170 megabyte, now it's only 4 megabyte. It is much smaller in space and it's much easier for me to email this data to another side of my collaborator or researchers. The magic is this. Once they have received this file, as long as they double click on this file, it will be able to go back to the original data set. It looks like a magic in computer science, basically. So how is that possible? How does all of this happening? And that is the things we want to discuss about the zip. So now you understand what is the zip, and let me continue to discuss about the ideas behind it. So origin file, the important thing about the zip is that it can become much smaller in the space, and then when the other side of the people who receives it, it will be able to retrieve the original data and get the full information out of it. So to discuss about the basic concept behind it, let's need to discuss about how this computer stores information. As you know, computers only understand 0 and 1. Everything is 0 and 1. So how is that possible? The computers can store a string or store a Word file or whatever files that it has. Basically, the easiest format is using what we call ASCII code, saying that we have a string that we want to store. It's ABRACADABRA, something like this. So how does computer store A? By using the ASCII code. So this is the table about the ASCII code. What it will do is that it stores all kinds of different characters, uppercase, lowercase, numbers, symbols, printable symbols, and some unprintable symbols. All of these are stored according to this table. So what this table trying to say is that, for example, if we look into the uppercase A, what it's trying to store inside of the computer in hexadecimal format is 41. So basically, if we're using the decimal numbers that we are looking, this is number 65. ASCII code is able to store 127 different characters. And therefore, if we strictly speaking, we need 7 bits to store, because 2 to the power of 7 equal to 128. Since there's only 127 different kind of characters, 7-bit is going to be good enough. However, current computers is using the byte as a unit, which 1 byte is equal to 8-bit. So basically, one ASCII code is being stored inside of a byte, so that it's going to be an 8-bit storage to store the information. And all of this will be mapped, all of these characters will be mapped into the ASCII code and then stored it. So every single character will require 1 byte or 8 bits to store the information. And therefore, since this string has 11 characters, it will use 88 bits to store the whole information. However, by looking into this string that we have, now let's talk about how do we make the space much smaller than 88-bit. Since by looking into this string, there's only 5 different individual characters. We don't need to actually using the whole ASCII map to map it. And therefore, if we try to say minimize the cost of storing the string, we will be able to notice that there are only 5 different words, and therefore, if I have 3 bits space, and we will be able to store all this kind of information. So take a look of this. Since we have 5 different words, we need 3 bits. If we only have 4, we only need 2 bits, which is going to save even more space. But since we have 5 different characters over here, saying that we create a code. So this is like a treasure hunt kind of coding system. So saying that A is going to be stored as 000, B is 001, C is 010, D is 011, R is 100. Every single character is stored in a 3-bit system with this key that we will be able to map. And of course, you need to store this key together with the file so that they can be decoded. So by using this, you can see that the whole 11-word string will be changing to A equal to 000, B equal to 001, C and R equal to 100. So this whole string, based on this mapping system, we require only 33 bits to store the information. In this way, we have saving from 88 to 33 bits. So it's actually a much smaller space already. This is the basic idea. Now, is there a better way to do so? Of course. Saying that magically, we have this mapping. So this mapping is different from the previous example that we see. In previous example, every word requires only to use exactly 3 bits. So when we try to decode it, we know 3 bits is 1 unit, and we will be able to map it and then decode it. However, take a look of the better example. A is using only 1 bit. R using 2 bits. B is 3, C and D is 4 bits. By doing this, one thing you may notice is that if we use this mapping, map the magic word, we would get this string which requires only 23 bits. And it is saving from 88 to 33. Now it's only 23 bits. So how does this magic happen? Of course, why? First of all, you need to understand why we can save even more. Because one thing happened in here is that A requires only 1 bit, which is the most frequent item, appeared in the magic word, while C and D using 4 bits, even 1 bit more than previous encoding schema. C and D occurs only once in here, so the frequency has been taken into consideration in this mapping. And so we want to discuss about how is this possible, how is this being generated through the topics we want to discuss today, which is the Huffman encoding tree. Before we even move into the Huffman encoding tree, you need to understand one thing. There is one very nice property of the Huffman encoding tree which showed in our previous example, with what we call a prefix code. To talk about this one, we need to look into a bad example. So in this example, saying A is mapped to 0, 1, B is mapped into 0, 1, 0, 1. Saying that we have this kind of encoding, now we can encode whatever words that we have, thinking, well, everybody can decode it as long as they have this table. In fact, it's not true, because saying that I have received a magic encoding message 010101, now I get confused, because this can be decoded as 01, which is A, and then 0101, which is B. Or this is BA, which can be decoded in the same way, or it's even AAA, because there's no way that I'll be able to distinguish from this one with the other one. And therefore, why this encoding does not work? Because the code word for A is actually a prefix of B. Because A is starting from 01, and B is encoded as 01, and B started as 01. And therefore, we will not be able to distinguish from one to the other. If we look into the previous example, you will understand that A is 0. As long as A is defined as 0, no other things will start with 0. And therefore, they will not having any problem to decode it. The same thing with R equal to 1, 1, then B nor C nor D started with 1, 1. In fact, they're starting with 1, 0. And therefore, this is the important property that we need to maintain so that we will be able to decode the information. So, any prefix code can be represented by a full binary tree. To satisfy all of these things, Huffman encoding tree is actually the tool for us to do so, and it will give you the prefix codes property. By looking into that one, each leaf node stores a symbol, and the nodes has 2 child. Left branch means 0, right branch means 1. The code word for each word is the path from the root to the leaf node. Let's take a look at this one. Saying that this is our Huffman encoding tree. This tree gives you the property of the prefix code starting from the root. If we travel to A, because we go from the left child, then we get a code of 0. If we travel to the right side, we get a value of 1. So from the root reaching R is 1 and 1 over here. So if we travel from the root 1011 to D, then D's code is 1011. Now you understand how do we use the Huffman encoding tree. The only question left is how do we build the Huffman encoding tree. Let's take a look at it. It is clear that the 2 symbols with the smallest frequency must be at the bottom of the original tree. This is the observations when we're using the frequency. The most frequent one, we want to keep it as close to root as possible so that we can have minimum codes. For the one that are least frequently used would be at the bottom of the tree. So this algorithm is considered what we call a greedy algorithm. And as long as you know that property, Huffman encoding tree is Pretty straightforward. Saying that we have a message that we want to encode, and it has 5 words as we see earlier. Now we have A appears 50 times. These are the frequency. For example, B 15 times, C and D 10 times each, R is 18 times. To build up a Huffman encoding tree, all we need to do is we find the smallest 2 values. This step, or this can actually be achieved through the binary heap concept. Because binary heap gives us the smallest value. So as long as we store all of this information, we can find the minimum. Very easy, 10. And if we delete that one, we can find the next minimum, which will get another 10. So we will understand C and D are 2 smallest value. And now what we are going to do is we can build the 2 things together to form a tree, the tree of C and D. And of course, this tree occurs 20 times, which is the sum of the C and D. Once we have done that, so you see now we have only 4 nodes, A, B, C, and D together, and R with 4 different nodes, and we repeat the same process. Find the next 2 smallest values. 50, 15, 20, and 18. We will understand 15 is the next smallest value. So we will take B out, finding another smallest value, 18, and then take R, put them together, form a tree. So now we have 2 trees. The next thing is that we keep doing the same thing. After we have done that step, we have 3 nodes, 50, 33, and 20. So we will find the 2 smallest value are these 2. So we will put these 2 trees together to form 1 tree. And finally, we can put all of the nodes together, put A combined with the previous combined tree, so that we will have this Huffman encoding tree. If we travel from the root, go to the right side is 1, then A, because it's the most frequent item, the code for A will be 1 based on this Huffman encoding tree, and we will be able to build up the whole Huffman encoding tree based on this approach. By looking into the path, travel path, we can encode each characters with their own code. You may notice one thing. The last step, when I put A to this whole tree, this is the tree of B, R, C, and D. All 4 things are being combined together. I put A on the right side, which makes A encoded as a 1. It is totally possible that I put A instead of the right side. I can put it on the left side. In that case, A will be encoded as the value of 0, still 1 bit. That's totally fine. And everything will have a little bit different encoding, but the number of bits to encode each word would be the same. So in this case, you will understand that Huffman encoding tree is not unique trees based on the given input. And therefore, if you using Huffman encoding tree to encode your message, you need to pass what the tree looks like so that the receiver can decode the whole message. Let's take a look of another example. This time we'll go a little bit faster. So assume the frequency of the symbols are this 1, 2, 3, 4, 5, another 5 examples, and now they have different frequencies. The only difference is actually the R, I can tell you that. So in this example, we try to find the 2 smallest elements, C and D together, so we put them together. Now, next one, we have A, B, C plus D together, and R. To find the 2 smallest value, it will be 20 and 20. So we will put all these nodes together. So you see that C and D will be combined with B over here. Again, you can see that B can be on the left side or on the right side. It doesn't matter. It's going to be your own choices because the representation of the bits would be the same. So once we put them together, you see now we have 3 nodes only, 50, 40, and 30. Since the two smallest value are B, C, D, and R, then we put them together. So we have this tree. Again, R can be on the right side or on the left side. It doesn't matter. Finally, we put a node together, and then we will be able to form this tree over here. By doing so, looking into the Huffman encoding tree, if we travel from the left side, we get a 0. If we travel to the right side, we get a 1. And we would be able to encode this whole thing as this Huffman encoding tree. That is the idea about how do we zip the file. Pretty amazing, and I want you guys to be able to understand it. The last slides I want to present to you before I give you the assignment is this one, saying that you receive, thinking about this, say you are a receiver, you receive this code. Of course, you have no idea what is this code going to be. You will need this Huffman encoding tree to map back over here, understanding what is the message hidden in here. So I want you guys to take a look. What is this message? What is the word stored inside of this binary code? So of course, the decoding result is BAD without this symbol. How do we know that? We're starting from 1 because it's starting from 1, 1, 0, 0. So we end up with here, which give you a B for the first 3 bits. Now, next one, we're starting from the root. Immediately we hit a 0, we know that's a A. And then if we go from the next one, 1, 0, 1, 1, we find a D. So we will be able to get our code. So finally, take a look of this assignment. Say now there is a message composed of 6 different words, and these are the frequencies given over there. I want you to work on the Huffman encoding tree. Show me what is the Huffman encoding tree looks like. You can of course draw on the computer, give me the file, or you can draw on pen and paper, use your phone, take a picture, and then submit that. Whatever you want to do is totally up to you, as long as you give me what's the Huffman encoding tree based on the frequency.